Please, make sure that you keep up on top of the assignments. Okay, so things are kind of picking up a little bit. I'm going to move a few of the due dates around so that it's a little easier. Okay. One thing I think I will do on Tuesday, instead of having a lecture on proportions, since we're not going to have homework and we're not going to be able to really get into that in any depth, I think on Tuesday I'll have a practice exam 3 in class. And that way you can get practice in class and we can go through it. And if you do that, I'll give you some bonus points on exam 3 also, okay? Okay, so this is the PowerPoint we're going to work off of, and I'd like you to open that up. And then we're going to work with 2 data files today. So one is called Dataset Regression Problem 2, and the other one's called Dataset Regression Used Porsche. And I'd like you to download both of those and open up StatCrunch, please. And just bring those into StatCrunch really quick, and then we can get started. Is the connection a little slow today?
Yeah.
Okay, it's not just me. All right. Wow, it really is slow. Okay, so while we're waiting for that, I'm going to go ahead and get started. It may take a little while to load. Here we go. All right. All right, there we are. And regression is a very general term. Wow, I'm just not getting anything to work today, am I? Give me 1 second. This is acting up a little bit. So regression is a very general term. And the idea behind regression is it's going to let us study quantitative variables, the relationships between quantitative variables. Notice we've only been working with one quantitative variable so far. Even with the 2-sample t-test, it's always the same variable, right? So now we want to look at more than one variable. And this is used in a lot of different things, okay? So whenever we want to start trying to establish a cause and effect relationship, we have to start with regression. So how do you, demonstrate that smoking causes cancer, right? We start with regression. For prediction, we're doing stocks, commodities, things like that. That's really important. And we want to model behaviors of complex systems. So this is where you start to get into this thing called machine learning. Prediction's a really big deal, okay? So this is the latest version of the magazine that the American Statistical Association puts out. And the cover story is this thing called Saving Bergen. So Bergen is a little town in Norway. And as you probably have heard, or you've heard rumors, water levels are rising. And so Bergen is experiencing these problems. And so they have to make a prediction. How high is the water going to rise? In other words, should they start to literally build a wall around the city or not? That's a lot of money, okay? So these are the sorts of things that they really occur every day. They aren't academic considerations. These are some examples of problems that we studied with, regression. So, advertising, relationship between advertising cost and profit, stock sale volume and price. What is the risk the person's going to default on a loan given their credit score? And these are the sorts of things that are going to affect you. These are how companies make decisions, okay? On things that are going to affect you. And so one of the things I want to do as we're studying regression is I want to look at it through the filter of the big picture of statistics. Partly because I really want to emphasize how important this is. This is fundamental to statistics. So if statistics was a religion and we had a Bible, okay, it would start off in the beginning, there was the big picture of statistics, and it was good. This thing is so fundamental. We have to have this. Think of it like a science, right? You couldn't have science without the scientific method. The same thing here. We have to have this process to do statistics. This is both a good and a bad thing. I mean, one of the things that's really good about this process, and I hope you kind of got some flavor for this, is how careful we are. So at the very beginning, we talked about context, right? We have to be really careful, know what it is we're measuring, where are we taking our data from. How we collect the data is really important. And we didn't even talk about that. But actually, when you go to do a real study, you have to sit down just like a chemistry experiment and plan how you're going to collect the data. That's a branch of statistics known as experimental design. When I first started off in statistics, I'll tell you a funny story, kind of related to this, to point out how important it is. I was doing a consulting job with a mathematician and a statistician. Both of them were very famous. And we were touring the company with the president. And at one point, he took us to this room with all this data, all these papers and all this sort of stuff. And he said, here's all the data I have. Isn't this great? And the mathematician went crazy. Oh, this is terrific. We can curve fit, we can do this, we can do that. And the statistician was silent. And the owner said, hey, don't you like data? You're a statistician, aren't you excited? The statistician said, I probably can't do anything with it. Well, why was he saying that? Because he was a jerk? No. He was saying that because he didn't know how the data was collected. He didn't know where it came from. He didn't know what the context was. And it's actually really important, okay? So the thing is, we're really careful, but it's both a strength and a weakness. And this is where it's a weakness. So notice, just when we looked at one variable, how hard it was to work with the probability model. I mean, first you had to get your mind around the sampling distribution. And then we had to worry about, was the data mound-shaped or not? And if it was, we had to use, the Z or the T, right? It was hard with just one variable. Imagine what it's like with 20, or like with big data, hundreds of variables, okay? And this is a problem. Statisticians don't know how to deal with big data. So very often people ask, what is the difference between big, data science and statistics? And the answer is, it's this big picture. And what the data scientists do, the statisticians don't, is they say, we don't know the probability distribution, who cares? And they just go right ahead. They say, we're just going to do stuff and see if we can come up with something useful. And they have, because they haven't tried to be as careful. They've just gone in and started digging in and finding stuff. And statisticians are kind of afraid because they don't really know exactly what they're doing. So now it's kind of to the point where data science is like applied physics, and statistics is becoming more like theoretical physics. We're trying to catch up and get more into the applied game. So I think this big picture is really useful. So, okay, we start off with a question, and the question here is going to have to be a relationship between two quantitative variables. And so this Porsche data set was something I was thinking about way back when. I wanted to know how the mileage affects the price of a used Porsche, okay? So this could be your question. What is the relationship between the quantitative variable mileage and the quantitative variable price? One of the cool things about statistics, I hope you take this away from this class, is the fact that you can use statistics to answer problems that you're interested in, okay? So this was something I was actually interested in, went out and collected data and tried to get an answer. Okay, so what do we have to do next? We posed our question, now we have to collect the data. So what are the principles involved with data collection? Well, we have to define where we're going to take our data from. What's our population of interest? Then we have to make sure we take a random sample. Why? Because we want our values to be accurate. So if you go back to that bullseye analogy, right? When you're randomly sampling, what happens? Here's your bullseye, and your shots are centered around the bullseye, right? And sample size is really important too. Because what sample size is going to do? It's going to control the spread. Larger samples tighter cluster, right? So random sampling and sample sizes are really a big issue. So what did I do to get this data? Well, I went to AutoTrader. That's as good a source as any, back in 2007. And I randomly sampled 30 Porsches. I made a list of all the Porsches, and I took 30. Why didn't I select them by eye? Why didn't I just go in and just pick out on my own Porsches?
Because we've proven in one of our activities that that's not the best way of selecting
So when humans select things, we tend to be biased. So what would happen? Well, I see a nice red shiny Porsche, right? And I probably pick that. And even when we try to be unbiased, when we try to sample uniformly, okay, we still end up being biased. So it's always best to let the computer do those sorts of things. And so anyhow, when all the computational smoke cleared, this was the data set that I got. And this is the data set I asked you guys to download. So if we want to understand this, okay, notice that there's two variables, right? So the one variable is the price. It's in thousands of dollars. So this last Porsche, right, it was advertised for $52,900. And this was the mileage in thousands of miles. It had 36,000 miles, 36,600 miles. Okay. And so we have data on these 30 pieces, 30 Porsches. Okay, so what do we want to do next? We have to summarize. No one can look at all those numbers and make sense of them, right? So what do? We always do the same three things. We plot the data, describe the plot, and then we compute numbers that describe, we compute numbers that kind of characterize these things we're describing. So a good thing to start thinking about and reviewing for the final is, what did we do with one variable? We made histograms, right? We reported the center and the spread, and we computed the mean and the standard deviation, right? So the really important things were how many modes, the center, the spread, right? And the shape. So what do we do with a data set here? So here's the thing that you want to be aware of, is that this is one data point, okay? For the first portion, both pieces of those information are one data point, which means now that when we go ahead and plot this, we're going to have to plot an ordered pair, right? And how do we do that? We plot that on an XY plane, right? A Cartesian plane. So here's the trick. We got to figure out which is X and which is Y. So the convention is that the thing we're trying to predict, we're going to call Y, and the thing that's predicting Y, we're going to call X. All right? So if you go back to this example, what would Y and what would X be? What is the thing we're trying to predict? Yeah, price and mileage. Are you trying to predict price from mileage or mileage from price? What do you think? Price from mileage. Okay, so the thing we're trying to predict, that would be Y. So Y would be price, right? And X would be mileage. And usually it's common sense. Usually it kind of makes sense. But sometimes it's a little tricky. And so when we go ahead and plot these XY pairs, we get this thing called a scatterplot. And it looks just like, kind of like buckshot, right? It's just points that are all scattered all over the place. How do we do this in StatCrunch? Well, before we get into that, I want to make sure that we know how to figure out which is X and which is Y. So sometimes these go by slightly different names. So this is the variable that we're trying to predict. And this is a variable we're using to predict. And the thing you want to be aware of is that sometimes we use slightly different names, okay? So sometimes we call X the predictor variable. I'm just going to use VAR for variable. Sometimes we call it the explanatory variable. Because it's the variable that, in a sense, explains the other variable. And sometimes we become a little more mathematical, and we call this what you probably call this in algebra, which is the independent variable. So we can go by slightly different names. Y, we tend to call the response variable. But sometimes we call it the dependent variable. So you may see these different names. Don't let them throw you. Usually the names are kind of self-explanatory, right? This is predicting or explaining y, okay? This is the independent variable. We always think of math as x being independent, y being dependent, right? So you may see that sort of terminology. So let me give you some examples, and let's see if we can figure out which is x and which is y. So suppose scientists want to study the relationship between a person's weight and their caloric intake. What would be x and what would be y here? Weight would be y and caloric intake would be x. I would agree with that, right? We're trying to predict weight. That would be y from the caloric intake. Okay. Unfortunately, there is a relationship, right? Okay. So you're a house hunter and you're interested in the relationship between the selling price of a home and its square footage. What do you think? What's x and what is y?
What is the selling price?
Exactly. We want to be predicting the selling price in the square footage. Good. Let's see. What would be x and y here? What do you think?
Interest rate would be y and x would be loan application.
Does everybody agree? I think this is one that could go both ways. I mean, I think the best interpretation is for y to be the interest rate and x be the number of loan applications. But on the other hand, you could argue that the interest rate drives the loan applications. Okay, so you could be using the interest rate to predict the number of loans. When we construct a regression model, actually it doesn't matter what we call x and what we call y. The model is valid both ways, but it's usually best to have the thing that you're predicting be called y. So here it would kind of depend upon what you want to do. Maybe if you're a bank, you might be interested in predicting interest rates from the number of loan applications, right? So you have to think about the context. But sometimes it can go both ways. On average, are men taller than women? What's x and what is y here? What do you think, Kathy? What's x and what's y?
Would gender be y and height?
So that's a really good question. Here we have two variables, but they're not both quantitative, right? So one is categorical, okay? So here we couldn't really use regression. This notion of x and y wouldn't make sense. How would we actually analyze this statistically if we didn't use regression? What's the better way to do that?
T-stats,
Right, I'm going to do an unpaired two-sample t-test to answer this, right? So this is not a regression problem. And here's the thing. So, it might seem like I'm being tricky, but I'm not. In real life, problems don't come wrapped up with a set of instructions saying, please analyze me doing regression. You have to figure this out. And very often what happens is people misuse regression. So a kind of classic example, and this happens a lot. People will do a study between education and income. And what they'll do is education is a categorical variable. Okay, so we'll have like low, medium, high levels of education, but they'll code it with numbers, 0, 1, and 2. And they'll treat that like it's quantitative. So they'll do regression, which is wrong. You can't do that. So you have to be careful about this, okay? All right, last one. This is like a bona fide exam problem. Now you guys are all warmed up.
distance from homes, that's
I would say that's correct, right? Degree of homesickness is going to be what I'm trying to predict how far away the car. It's not the other way around. Right? I'm not trying to predict how far they are from the homesickness. Good, good. So okay, so this is a actual homework problem. I'd like you to read this and think about what is the x and what is the y variable here. There's actually a phrase here. There's a word that kind of tips you off. What is the word here? There's one word that kind of tells you. Predict. Predict. So this is kind of what's cluing me in, right? So what will be my y variable here? Okay, let's see. So y is the number of units sold. And then x would be what? Good. Number of full-time employees. Yeah. All right. So I'm trying to use this to predict this. Good. Okay, so now let's look at the possibilities. So the explanatory variable or the predictor variable, what is that? Is that the x or the y? What is the explanatory or predictor? Is that x or is that a y? It's x. It's got the x, okay. So we know that the explanatory is a number of full-time employees. So we can automatically rule out A and C, right? Because they're saying the explanatory variable is the number of units sold, which is y. So which one is it, B or D? They both start off saying the explanatory variable is the number of full-time employees. D. How do I choose between B or D? What is the difference?
D, because it's talking about the units depending on full-time employees.
Right. So if you have to look at the rest of the statement. So the reason why B is wrong is because they're saying the executives want to know how full-time employees depends on units sold per month. So that's saying that they're predicting the number of employees from the units. That's not what we're doing, right? We're predicting the units sold based on the number of full-time employees. So that's why it's D over B. So you have to be careful. And sometimes this ticks people off about statistics. They say, oh, you know, you're so tricky, the wording is you have to watch the wording. But it's true, it is. Think about the hypothesis test when you draw a conclusion. What is the difference? It's one word, not. Right? There either is sufficient evidence or there is not sufficient evidence. So words are important, okay? You really do have to read carefully. Okay, so the response variable we know is the units sold per month, right? So the same thing, you have to be careful, right? Do they want to know how the number of full-time employees depends on the number of units? No. They want to know how the number of units depends on the number of full-time employees. So it's going to be A. And finally, what do we plot on the y-axis? We plot the response variable, the number of units sold. Do we have any questions on those examples? Everyone's good? All right. Okay. So now we're ready to do the plot. So here's what we're going to do. We're going to go into StatCrunch, and under Graph, just go to Scatterplot. And there's three things you have to fill in. Okay, first of all, you need to enter the variables in the right order. Okay. So mileage is going to be the x variable, price will be the y. Then notice this thing called overlay polynomial order. We're going to choose 1. We're going to go ahead and choose 1 in there. And then finally, you're going to add titles and labels. So it looks kind of like this, right? Let's see, where's my StatCrunch? Oh, here it is. Okay, so go ahead and load your data. So you'll do graph, scatterplot, mileage, price, overlay polynomial of order 1. Now, one thing that helps a little bit, because sometimes the points and the lines are a little bit light, you might want to increase the point size to about 4 or 5 and increase the line size to about 4 or 5. Then you can kind of see what's going on. Okay. And hopefully you got something like that. And because this is such a fundamental part, it's good. I just want to make sure everyone's good on that. Yeah. Huh? Okay, so you have your x and your y. So your x is going to be, so your x will be mileage, right? Your y will be price. And I'll overlay polynomial order 1. Okay. And you should be good. Yep. All right, good. That was so good. It's an optical illusion. It looks curved. It is. Okay, interesting. It looks kind of curved. So, excellent. Good, good, good. Okay. They did. I thought. Okay. Yeah. Okay. So let me find out for you what's going on a little bit. I thought I understood, but maybe I don't. Okay, good, good. So this is our scatter plot. This is what we're going to work with, all right? So is everybody good on that? Any questions or problems that we're having? Everyone's good? All right. So now we have to figure out how to describe the plot. So here's the idea. What we're doing is we're trying to look for a trend in those points. And in our mind's eye, we're going to try to draw a curve through that trend. If you think about it, whenever we plot data, even for one variable, what do? When we plot a histogram, we try to draw a nice smooth curve, right? And we do the histogram. We're going to do the same thing with these points here. And there's 3 things that we want to report. First of all, we want to figure out what type of curve, what sort of line do these points seem to follow? Now, there's 3 possibilities. The first is that there's no relationship at all. And you'd be surprised at the number of things that you think are related that aren't. Classic example is basketball. If you look at free throw percentage versus winning percentage for a team, there's no statistically significant correlation, which is really surprising. You would think there would be, but there isn't. So it could be linear. In other words, the points could follow on a line, or it could be something else. Quadratic, or it could be more complicated. If you think about, for example, fitting sails for things like snowshoes, what is that trend going to look like? It's going to be seasonal, right? So it's not going to be any of the above. Okay, if the trend is linear, we can talk about 2 things. First, we can talk about the direction. In other words, does the graph seem to be going up or does it seem to be going down? Okay. And last, we can talk about the strength. And that has to do with how tightly the points are clustered around that trend line. So remember when we looked at one variable and we were talking about modes, we kept it really simple. We said, how many modes? There could be none, 1, 2, or multimodal. We do the same thing with relationships, okay? This is no relationship. In other words, these points don't seem to follow any sort of trend. They're just a cloud, right? This is a linear relationship. The data points clearly follow on a line. This is a nonlinear relationship. There is a pattern, but it's not a nice line, okay? So if it is linear, then we want to know 2 things. We want to know what is the direction of the trend. In other words, as x goes up, does y seem to go up? So notice this trend line here at the positive slope. Same here, same here. These are all positive relationships, okay? This is negative, meaning the trend line goes down as x goes up. All right, same thing here. What's an example of a positive relationship? Anyone give me the example of a positive relationship?
Work experience.
What's that?
Work experience and pay.
Yeah. So, as work experience goes up, pay tends to go up. Notice that this is not absolute. We're not talking about the data values. There are some people that have worked at a job for 20 years and make really low pay, right? But this is a trend. It tends to be the case, right? What about a negative relationship? What's a negative relationship? What do you think? Negative relationship.
Trying to think of one off the top of my head. I suppose mileage to price. We're gonna go by that.
Okay, so the Porsche data, right? As the mileage on the Porsche goes up, right? The price goes down. Good. All right. Now notice what we're talking about. We're talking about strength. Okay. So these are strong relationships, meaning that the data points are really tightly clustered. This model is really good at predicting, right? There's not a lot of error. This is, a moderately strong relationship. Notice that the data points still have a trend, but they're more scattered out around the line. And these are weak relationships. Again, there's a definite trend, okay, but there's a lot more scattered. How do you know which is which? We're going to calculate something called a correlation coefficient that actually tells us both pieces of information. But here's the thing I want you to think about. Most things in real life, do you think they're like this, or this? And we're talking about like real life problems. You have a real life variable, and you only use one other variable to try to explain it. What do you think it's going to be, Jason?
Like weak, mostly or sometimes moderate.
Weak or moderate. This is something to think about. You see issues in the news like this every day. The school shootings, right? What happens? Everyone has their idea. They think it's one thing. So one person says, oh, we need increased law enforcement. Another person says, we need this, we need that. Very few things are explained by a single variable. So most of these end up being this. It was interesting, right after I had that consulting job with those two guys, I had another job with a woman who was from Harvard. She was doing her master's in environmental science. And she was trying to predict how much trees grow in some island in the South Pacific based only on minerals. And Harvard did an incredible job. They split this island up into these really nice cells. They randomly sampled. They did a really good test of all the minerals. And she hired me to analyze it. And she said, don't you think we're going to get great results? And I said, no, I don't. And she fired me. She thought I was being negative. I tried to explain to her what happened. She said, well, I said, you only have one variable. She said, no, we have 23 minerals. I said, right, they're all of the same type. So, when you're looking at things, and you guys are going to have these sorts of situations where you're dealing with environmental issues, like tree growth is dependent upon minerals, but what else is it dependent upon? A ton of things. Sunlight, water, wind, animals, insects, fungi. These all play a role. And she called me back months later and apologized. She said, yeah, I was right. She fit like 30%. She was kind of like somewhere in here. But this is very commonplace, okay? So, what does that mean? That means that you generally have to do regression with more than one variable, which we're not going to get into, unfortunately. Okay, so here's the data set that we have for the Porsche. How would we describe this? Is there no relationship, a linear or a nonlinear? What do you think? What do you think, Thomas? Linear, no relationship? I would say linear, right? It's definitely not no relationship. It's not just like a nebulous cloud, right? And I don't see like any more complicated pattern than linear. I don't see any curves or anything like that. Okay, so it's linear. What is the direction? Positive or negative? Well, let's call this as negative, right? Is this a strong, moderate, or weak relation? This is a little bit of a judgment call at this point.
Moderate.
I'd say moderate is probably pretty accurate. So how do we make these things quantitative? All right. Well, we're gonna see in a second. So let's go ahead and open up. This is the data set that's called. Where is it? I haven't downloaded it yet. This is the data set that's called problem 2, right? let's go ahead and download that. Does everyone know the problems, the data set I'm referring to? Everyone's good? So it's data set regression model, data set regression problem 2, my stat lab. And I'd like you to download this. Make the scatter plot, right? And we have to figure out which is X and which is Y here, right? Before we can do anything. So sales versus number of salespeople. What should be predicting what, do you think? Should the number of salespeople be used to predict the sales, or should the sales be used to predict the number of salespeople? What do you think? Yeah. One thing you can do, really cool thing is this kind of like Excel, right? You can just do like this and drag it, right? Kind of see what's going on there. I would probably say it's number of salespeople is going to predict number of sales, right? So let's go ahead and make number of salespeople the X variable and sales Y. And we're always going to use polynomial of order 1. So go ahead and make that plot and then try to answer these questions. And after we do that, we'll take a short break. And if that's kind of small, I'll blow it up. But this is in the PowerPoint notes also if you want to take a look at it. Here, I'll try to blow it up. So what are we looking at? We're looking at the type of relationship, direction of the relationship, and the strength. So what do you think the type of relationship is? How would you classify this? So let me ask you this: who wants to describe it all in one sentence? Go ahead.
Positive, linear, moderate. Yeah, I guess it's pretty strong.
I might say it's a strong linear positive. Yeah. And we haven't talked about how to know if it's strong, but these points are, for the most part, pretty tight and tough. Strong positive linear relationship. You can say it all in one sentence. Okay. The order doesn't matter, all right? Positive, strong, linear. All right, good deal. Let me just check really quick. Was there anything else with that problem we wanted to answer? Does a scatter plot show any outliers? So here's kind of what's going on with the outliers. We're going to talk about this a little bit, but not very much. So we talked about outliers in when we had a single variable. And here's kind of what they mean. So you have some scatter plot like this, right? And so this is the range of x values. Sometimes you'll get an x value way out here. This is an outlier in x, meaning he's separated from the other ones. So let me ask you a question. Suppose this is the regression line, the best fit line with these data points. What do you think the effect of this point is if it was added to the data set and I was asked to recompute the regression line? what do you think would happen to the regression line? It would definitely affect it, and here's what actually happens. It ends up rotating it. So when you have this, it would actually end up kind of rotating this line, right, down towards here. So sometimes we talk about something called leverage. This is kind of like leverage, right? It's going to move this line and rotate it. Now notice this is the range of y values. So sometimes we have a y value way up here. That's called an outlier in y. And you can have both. You can have a point way up here. This is an outlier in x and y. And both. And what this does really depends upon where this is. If this was here, it would tend to raise the line up a little bit, okay? That's kind of the idea. So sometimes here's how we say something. If we wanted to describe that last plot, and we wanted to say that there weren't any outliers, we say that the data shows a strong positive linear relationship. There's no other remarkable observations. That's another way of saying no outliers. Okay. All right, why don't we take a quick break? We'll come back. What time is it now? 4:27. We'll come back at 4:32. Okay, about 5 minutes. And once again, we will start with you, and we're all when we return. All right, thanks. Mm-hmm.
Most of the time,
I have all your stuff graded. I need to give it back.
Oh, it's there's a question there. You know, so I'm sorry. You know, the control projects you know, so it's not the volume of people who design search down to it.
Yes.
So what you do, yeah, just check.
Yeah, you go.
I do have so I can answer the questions from mine, but then it's kind of like it could be me putting in numbers and influence it.
I think if a person looked out from the outside, you'd say that you're something like
Yeah,
even though it's only one data point.
just checking.
That's a good question. Okay, so here's what we want to do. So we plotted the data. We know how to describe it. Now think about what we did with one quantitative variable. What did we do? We computed these things called summary statistics. What are summary statistics? What is a statistic, first of all? This is a definition you've definitely got to know for the final. There's no way you're getting through statistics without knowing what a statistic means. What is a statistic? Something we compute from data, right? That's what a statistic is, okay? So the old joke is, they say don't drink and drive and become a statistic, but you can't become a statistic. You can become a data point, but you can't become a statistic, okay? This is something we compute. Now, when you did the homework on the t-stats, notice they asked you with summary, right? What were you putting in? You were putting in the summary statistics, right? The sample mean, the sample standard deviation. So these are numbers that characterize the population, right? So here's what we compute from regression. We don't compute anything at all like we did with one variable. We compute what's called a correlation coefficient, and we compute what's called regression coefficients. So what are these things? Okay. Well, first of all, to get them, we go into StatCrunch. So I'll tell you what, let's just stick with the Porsche example. We'll go with that data set, okay? And we're going to go to Stats, Regression, Simple Linear. Simple linear means we're working with one variable and we're looking at a linear function of that one variable. Now you're going to see a menu. When you click on simple linear, this is the menu that will pop up. It's a huge funking menu with a lot of stuff. We're not going to deal with anything except just putting in X and Y and compute. Later on, we'll deal with some of the bells and whistles, okay? But for right now, so you're in the Porsche data set here. Okay, do stat, regression, simple linear. And just like you did for the scatterplot, you're going to put the same X variable in mileage and the same Y variable price, and that's it. We're not going to worry about anything else. Now, you see the output for regression is a lot more involved than the output for any of our one variable tests, right? Whether we were doing t-statistics or whatever, this is a lot more complicated. And we're going to go into what these things mean. But just for right now, we only want to look at two things. Oops. We want to look at where it says, and we want to look at where it says estimates for the. So this is what we want to focus on. We want to focus on where it says regression, correlation coefficient. So here it's minus 0.8903. And we want to look at the estimated intercept and the slope for the line. Okay. So remember, we want the equation for the line, we need the y-intercept and the slope, right? These are the estimated values for the slope of the y-intercept. And that's what we're going to work with right now. Okay, so here's the cool part. What is the correlation coefficient? Well, the correlation coefficient tells us a lot of stuff. The sample correlation coefficient is always denoted by the letter small r. Just like we reserve small n for what? What does small n stand for? Sample size, right? Okay. Small r stands for sample correlation coefficient. And it tells us two things. First of all, the sign tells us whether we have a positive or negative relationship. So when the correlation coefficient is positive, we have a positive relationship. When it's negative, we have a negative relationship. And so if you look at this plot, so suppose you were given this scatter plot on a quiz or on an exam, and I asked you, what is the sign of the correlation coefficient? What would you say here? Right. I have a positive relationship, right? The trend line's going up, so the correlation coefficient is going to be positive. All right. And if I had this, obviously, this is a negative relationship, right? The trend is going down. So negative relationship, the sign of R is going to be negative. Now, one thing about the correlation coefficient that's always true is that its value lies between -1 and +1. And so the size of the correlation coefficient tells us the strength of the relationship. So when the absolute value, the magnitude of the correlation coefficient is near 1, this is evidence of a strong relationship. When the absolute value is near 0, this is a weak relationship. All right. So suppose I gave you these two plots and I told you that one had a correlation coefficient of -0.3 and the other had a correlation coefficient of -0.8. Well, this is a weak relationship and this is a strong relationship. So which one of those R values should go with which?
-0.3 should be on the left. -0.8 should be on the right.
So what if I said I disagree with you? And the reason why is because this is a stronger relationship and this is less than this. So shouldn't the -0.3 be here and the -0.8 be there?
No, it's the absolute value.
Right, it's the size, right? So the idea is that this should be -0.8 because this is a stronger relationship. And when we're talking about the strength of the relationship, we're not concerned about the sign, right? Whereas this is the weaker relationship. This R value has a smaller magnitude. Good. So -0.8, -0.3. Good. Okay. Finally, okay, so let's go ahead and answer this. This is another practice problem like in the homework. So the problem says assume the conditions for correlation are met. We're not going to worry about that for the moment. It says in the following statement true or false. If it's false, explain. So it says a correlation, and they really mean a correlation coefficient of 0.92 indicates a strong positive association. Is that true or false? What do you think? It's true. Does everyone agree? It's a positive relationship because the correlation coefficient is positive, right? And it's strong because the value is close to 1. Now, one thing I'll just mention, this is being a little nitpicky. The word association and correlation, they're not technically the same. Usually association is what happens when we look at the relationship between two categoricals. Usually when we're talking about two quantitative, we just say relationship or correlation. So, and you notice that they get a little sloppy. They actually start to kind of mix words. So usually we don't use association when we're talking about regression or two quantitative. But people do. Okay. So just a really quick review of linear functions, okay? This is a linear function, it's a line. Okay. So m is the slope of the line. Tells you how much y changes if x increases, right? So it's the rise over the run. So it's saying if we stay on the line, right, as we increase x by 1 unit, how much does y increase, right? And so this is all kind of review from algebra, right? Positive slope means you're going uphill, negative slope means you're going downhill. And the y-intercept, there's two ways of thinking about it. There's a geometrical way, right? So geometrically, the y-intercept is where this line intercepts the y-axis. Or algebraically, you can think of the y-intercept as the value of y when x is equal to 0, right? So if you put x equal to 0 in that equation, what do you get? Y is equal to b, right? And they're the same, they mean the same thing. Now, I want to make just one observation, which is we use some notation that sometimes can seem a little unfamiliar. So when we're dealing with lines, okay, we have different notations here. So if you think back to algebra, right? The equation for a line is y equal mx plus b. And so we use b to denote the y-intercept, right? This is the constant. And m denotes the slope. When we do regression, we use a different type of notation. So when we're doing regression, the regression line you get is b0 plus b1x. So notice the thing multiplying x is b1, b sub 1. And the constant, which we call b in algebra, now becomes b sub 0. And I point this out for a reason, because this b and these b's have nothing to do with each other. They're different b's, okay? And b0 and b1 have nothing to do with hypotheses, okay? This is the coefficient that goes with x to the 0. That's why the 0 is there. This is the coefficient that goes with x to the first power. Okay, that's where those come from. All right. There's one other observation I want to make about the regression line. It's not obvious, but it's very important. When we plot this regression line, so our data values, if you think about the Porsche example, right? Our data values are going like this, and this is our regression line. And notice that we don't write y, we write this thing called y hat. Now, it's really important to understand what this regression line means. This regression line represents the average value of y. So this thing here, sometimes called the fitted value of y, what it means is this represents the average value of y. This is what it means. And I want you to think about that for a second. Okay, why does that interpretation make sense, all right? So we can prove it mathematically, but here's why it makes sense. Suppose, for example, I look at 5 Porsches that all have 30,000 miles on it. Are they all going to have the same price? Of course not, right? There's going to be some scatter, okay? So maybe one is up here, one is up here. They look like this. So it makes sense that the value I should be interested in is really the mean value, right? So I should be interested in this mean value. So that's where that line should go through. Now, appreciate the fact that you've gained some sophistication here. When we used to talk about the mean, what was it? It was a single value, right? When we talked about one variable, we said mu was a fixed number. Notice now that we're saying that the mean's a function of x. The mean of y is a function of x. That makes sense, doesn't it? Average price for the Porsche should be a function of mileage, right? So now you're a little more sophisticated. You're thinking of the mean as a function now. It's no longer a single value, all right? So how does all this work? Okay. So in regression, this is how we write the regression line from the data. B0 is our y-intercept, right? B1 sub 1 is the slope, and y hat's called the fitted value. That's the average value of y. Now, this is something a little tricky. have to interpret these coefficients. They aren't just things that come out of a computer. So notice that how we think about this. When we think about the y-intercept, right, what was our y-intercept? If we go back to our model, right, this value was what? It was 70.6238. This was B naught. So what is the interpretation of B naught? So B naught is equal to the average value of y when x is equal to 0. In other words, in our model, this is the average value for the Porsche when it has 0 miles on it. Now let me ask you a question. So what we'd be claiming here is we'd be claiming that for a Porsche with 0 miles on it, the average price would be $70,000 in change, okay? Would be $70,000, $623.08. That's the interpretation. Is that correct? Here's what you want to notice. If you look at the data set, and this is something that you wouldn't know unless I told you, because this takes a little bit of observation. The x values go from 0.7 to about 92. In other words, we have one Porsche that has 700 miles, one that has 92,000 miles. Notice what I'm doing. I'm using the model to predict the y value outside of the range of x values, right? So 0 is not in my data set. Can I do that? Is that valid? So here's the thing. We're not supposed to do this. This is called extrapolation. And you might say that's stupid because 0 and 0.7 are so close, right? Why can't I just extend that line a little bit up? What's wrong with that in this problem? Why is that definitely wrong? This is a model for predicting what? Prices of what types of Porsches? Used Porsches. What is a car that has 0 miles called?
Brand new.
It's called brand new. Is this model appropriate for a brand new Porsche? Absolutely not. You guys all know when you drive a Porsche off the lot, what happens to the price? Boom, it goes down, right? So this is not a valid interpretation. So here's the problem. Whenever we want to start to use x values that are outside of the range we use to construct the model, we usually shouldn't do it. And this is the great moral tale, because it looks so close, and yet it's very wrong to do. Okay? So here, the y-intercept actually does not have any interpretation. We can't use it to say this. So this is an invalid. Even though it looks like this is what it is, this is an invalid interpretation. Okay. The slope, so here's a little bit trickiness too. The slope is usually the change in y over the change in x. But what is y here? It's the average price, right? So this is a change in the average price per change in thousands of miles. The two words that you want to be really careful about are these words, estimated and average, okay? So this is the estimated change in the average value of y per unit change in x. So who wants to interpret what this B1 value, this estimated slope ends up being what? Minus, can somebody read that off?
Minus 0.5806.
How do we interpret that? This does have an interpretation. Yeah.
For every mile the car gets added on, we predict it will lower an average of X dollars.
Actually, it's like this 0.506. Okay, so we have to be a little careful though, because what are the units here? So you're right. We have to be a little careful with the units. When X increases by 1, is that 1 mile? What is it?
It's thousands of miles.
Right.
Yeah.
So what we would say is that for every increase in 1,000 miles, the price goes down. And what's the price? And it's in units of what?
Thousands of dollars.
Thousands of dollars. The estimated decrease in the average price is $580.06. It just happens to work out that they're both in thousands. So you actually could say this. You could say for every extra mile added, the estimated average price goes down by roughly $0.50. So that also works. But you got to be careful about the units, right? All right, good. So any questions on, I know kind of going back and doing lines is something, you got to go back and bring back that algebra, right? So any questions about anything about lines? Anything on regression models? Everybody's good? Okay. So last thing we want to talk about very briefly today is this probability model. So notice what goes into the probability model, assumptions go into the probability model. So when we get together on Thursday, what we're going to talk about is we're going to talk about the fact that what we need to use this regression model is all these little deviations, okay? This difference here is called a residual. So the residual is equal to the true value of y minus the fitted value. And it turns out that all these little residuals, when you look at them, they have to be normally distributed. So now we're back to using a normal distribution. So what are we going to do? We're going to look at these residuals. We're going to plot them, right? Histogram, QQ plot, Shapiro-Wilks test, all that stuff we used before. Okay, it's going to come to bear when we look at regression too. And that's what we're going to talk about on Thursday. All right. So, try to read ahead in the PowerPoint notes and try to make sense of that, and we'll come back and finish this up on Thursday. All right, thanks.